Hello everyone, this video is on Unit 2, Standard 1, and it's how to determine limits. We're going to go over three types of limits and how to solve them. One is graphically, one is algebraically, another one is for piecewise functions. Again, this should be all review for you all since it's from Calculus AB, but in case you forgot, we're going to go over it one more time. Three basic definitions you need to know: left-hand limit, right-hand limit, and the general limit. The left-hand limit usually has an annotation, and it has this little minus sign right next to the number. So it's like as x goes to some number minus. That means the limit as the function as it approaches it from the left. Okay. If it's approaching from the right, it has a little plus sign next to the number, and the general limit has no sign next to it. So I'll highlight that, and that says read the limit of the function as x approaches c, which is right over here. So now let's look at some examples. Again, this should be review from last year. Let's look at this first problem. If you look at this column over here, let's start with these zeros down here. So you may notice in the second column you see a whole bunch of zeros. Let's start with this one. This one says as x approaches 0 minus, 0 plus, and 0 in general. Minus means from the left, plus means from the right. 0 by itself means if the minus and the plus are equal to each other, then it's the same answer. So let's look at 0. So here on the y-axis is where, as you'll agree with me, x is equal to 0 on the y-axis, right? Now, as I approach x equals 0 from the left, as I'm approaching x equals 0 from the left, do you see from the left I hit y equals 4? From the right, you may notice if I go across, and I hit x equals 0 from the right, I also hit 4. So that means, going back to my original problem, from the left is 4, and from the right is 4. And again, 0, the general limit, means if the left and the right match, then the general limit is also the same number. Okay, let's move on to, let's go back a little bit. It's maybe hard to see, but this says -5 minus, -5 plus, and -5 in general. So let's go back to the picture again and look at what happens at -5. So here's my graph. Here is where x equals -5. Okay, so I'm going to trace the graph, this line over here. I'm going to trace this line coming from the left. So from the left, I'm going. When I hit x equals -5, I hit, if you want me to highlight it for you, I hit y equals 1. Okay, from the right, let me undo that. From the right, if I follow this line, from the right, I'm going from the right until I hit x equals -5. I hit this white dot, and I also hit a number. This time it's not y equals 1. It is y equals -2. Okay, so from the left I hit y equals 1, and from the right I hit y equals -2. So going back to my problem, I'll write down 1 and -2. So you see how these two numbers don't match? In the other example, they all match, so it was the same. So since these don't match, I'm going to put does not exist. The limit does not exist, just like they say in Mean Girls, because the left and the right limits do not match. Let's move on to the next one. I got 2 minus, 2 plus, and 2 in general. So I'll go over to where y equals 2. I found it. Here's where where x equals 2. And let's trace the line from the left and from the right. From the left, I trace it and I get into y equals 0. From the right, I trace it. I also get y equals 0. They both equal 0. So you may notice that for this particular case, from the left is 0, from the right is 0. The general limit has to be 0. Now, just so you get to see the pattern here, if you have a chance or have an instance where the line, let me zoom in, where the lines from the left and the right connect, you know you're going to get a general limit. The one that we just did, they still connect. I get an open hole there, but still the two lines from the left and the right, they still connect. The example that we did where they didn't connect, so you see this example where they don't connect, I have a gap, that tells me that for sure my limit is not going to exist. And then our last example, 5 minus, 5 plus, and 5 in general. So let's go over to where x equals 5. Here's where x equals 5. Let's trace some lines. Now, from the left of 5, this line goes all the way up, and there's an arrow to tell me that it's going all the way to positive infinity. To the right of 5, if I trace my line, it goes all the way to negative infinity because it's pointing, has an arrow going all the way down. So to the left of 5, I have a limit of positive infinity. Okay. To the left of, to the right of 5, again, you notice that to the right of 5, I have an arrow going all the way down. That's negative infinity, which means the general limit does not exist because the two values do not match. And again, my little shortcut, I told you, you see how these two lines over here do not connect. This arrow, they're not connected. There's a break. That means I knew in advance that the limit was not going to exist. And two other ones that are most difficult for most people is the limit as x goes to negative infinity and as the limit goes to positive infinity. Okay, these two type of problems a lot of people have a difficulty with. Let me explain. Let's start with the limit as it goes to negative infinity. What I'm saying is when x goes all the way to the left, as I go all the way to the leftmost of the graph, where is my arrow, where's my graph, where's my function going? So if I look at my messy graph again, where's my leftmost function, or where's my leftmost arrow? It's right here, okay? This is where my leftmost part of the function is going. And you see how it's an arrow touching this line? That tells me as x goes to negative infinity, it's going to get closer and closer to this line, and this line is y equals 3. So really limits, I forgot to mention this, limits is when x is a number, what is the y going to be? So when x is going to be negative infinity, when my x is all the way to the left, my y is going to be at 3. Now, what if the limit as x goes, what if you're trying to find the limit as x goes to positive infinity? Instead, I'm going to look at my rightmost arrow, and you'll notice in this problem, my rightmost arrow is right here. This does not have a line, like the last one. See here, I have a line here, but this one does not have a line. This one's going all the way down. So if I trace my graph again, this one goes all the way down. So that tells me when x is infinity, when x is all the way out here, my y value is going to be all the way down here, or negative infinity, because that's where the graph is going. So that is negative infinity. So that is how you find limits graphically. Again, I'll go over it more in class, but that's how you do it, and should be a review from last year. I'm going to jump to a couple pages. Here's another example problem. I'm going to jump to the part that says section B. Now, how do you solve limits? We just did it for a graph. How do you do it algebraically? It's very simple. All you do is plug in the number that you see. So in this very first example, it says find the limit of x plus 7 over x squared minus 1 as x goes to 2. If I was doing this graphically, I would look at a graph and see from the left, see from the right again. But in this particular case, I do not have a graph. So all I do is take my number, 2, and I plug it in everywhere I see x, because that's the limit as x goes to 2. So I get 2 plus 7 on the top. I get 2 squared, which is 4, minus 1 on the bottom, which gives me 9 over 3, and simplifying it gives me 3. Okay. See another example. This one I have limit as x goes to negative 1. This time I have 3 x's, so negative 1 is going to go into this x, and this x. Okay. Negative 1 squared is 1, plus a negative 1, which is minus 1. I'll plug negative 1 into the denominator, I get negative 1 minus 5. So on the top I get 1 minus 1, which is 0. On the bottom I get minus 6. Now this is where a lot of people get confused. If you have a 0 in the numerator, then that fraction is equal to 0. If you have a 0 in the denominator, you have an undefined answer. You can't divide by 0. But you can divide 0 by a number. So that's why the answer is 0. I'm going to skip over this middle section right here so you can cross it out. And let's do some more examples of direct substitution. Now, this is where it gets tricky. They aren't always as easy as I showed you, and those of you that took calculus last year know that none of them are that easy. So let's look at this one, limit as x goes to 3. Again, I don't have a graph. And again, I'll take 3 and plug it everywhere I see x. 3 squared is 9, and 3 minus 3 is on the bottom. Doing my basic algebra, I get 0 over 0. Now, I told you earlier 0 divided by a number is 0. And I also told you earlier dividing by 0 is undefined. But what happens when you have 0 over 0? 0 over 0 tells you that there has to be a, you have to factor, you have to cancel, you have to do something to get rid of the 0 over 0. 0 over 0 means there's still more work to be done. There's three things you can do when you get 0 over 0. Here's the first one. It's called factoring. Now, back to my original problem. If I could erase everything, you could keep it on your paper. But you try, and if you get 0 over 0, first thing you want to do is try factoring. The top, you may have forgotten, is a difference of squares. I could factor that into x plus 3 and x minus 3. On the bottom, I keep my x minus 3. Now you notice, on the top I have an x minus 3, on the bottom I have an x minus 3, which means those two cancel, which leaves me with an x plus 3. So this whole problem can be simplified just to, this fraction means the exact same thing as x plus 3. Now, since I canceled something out, I will plug my 3 in, and 3 plus 3 is equal to 6. So in this particular case, again, factoring, this means you need to, if you get a 0 over 0, you need to do something to simplify the problem. Let's jump to these bottom two. First one, it says as limit as x goes to 0. You could do this in your head. If I plug in 0 into all of these, 0 here, 0 here, 0 here, and 0 here, I'm going to get 0 minus 0 over 0 plus 0. You should know I'm going to get 0 over 0. Now, some of you may just say like, oh, why don't I just factor in the beginning? You should always try plugging in the number because you never know if you're actually going to get a solution. So I plugged it in, I get 0 over 0. So that means I got a factor. In the top one, they both have, or the numerator, I have a common factor in x. So I'll factor out an x. Same thing with the bottom. I also have a common factor of an x. So now I have an x on the bottom and an x on the top, which means these two cancel. Because something cancels, now I'm going to try plugging in the 0 again. If I plug in 0 into the numerator, 3 times 0 minus 1, I get a minus 1 on the top, and the bottom I will get a 2. So my answer is negative half. So for sake of time, I'm going to skip over this bottom one. Actually, no, let's do this bottom one because that's a special case as well. Let's try plugging in 7. So 7 goes everywhere there's an x, so 7 goes here, here, and here. Okay, I get 49 minus 35 minus 14, which give you a heads up that equals 0. If I plug plug 7 into the bottom, I'm going to get 21 minus 21. So yes, spoiler alert, it's 0 over 0. Okay, so now I have 0 over 0. That tells me I got to simplify somehow. So I'm going to erase this. Again, you could keep it on your paper, it's just that I don't have a lot of space. And I need to factor. On the top one, you have a trinomial. So I know I'm going to have to factor the old-fashioned way like so. I need two numbers that if I multiply, I get negative 14, but if I add them, I get negative 5, which is going to be minus 7 and plus 2. Okay. On the bottom, my common factor is 3. So I get 3, and I get 7 minus x. Now, if I look closely, it looks like these can cancel, but they're not exactly the same. Almost the same, but not quite. When you have a case where you have two terms that almost look like they could cancel, that means you have to factor out a negative 1. So to make it easy, let's say on the bottom in my denominator, what if I factor out a negative 1? So I'm going to factor out a negative 1. Top stays the same. I'm going to take out a negative 1, so this becomes negative 3. 7 now becomes negative 7. Negative x now equals plus x. That's how you do factoring by a negative 1. Now, these two are exactly the same. They're rearranged, the negative 7 is out in front, but they're still the exact same parentheses, which means top and bottom will cancel. Which means this whole problem can be simplified into x plus 2 over negative 3. Because I canceled something, again, I'll try plugging it in. In this particular problem, remember it was 7, so now I'll plug in 7. I get 9 over negative 3, or negative 3. So that's how you do it with factoring. Two other possibilities that you can have. One is called rationalizing. So the whole thing was about factoring. What about if the problem was not factorable? Like in this case. I have a 4. I will plug in 4 into both of them. Top, I get 12 minus 12. Bottom, I get 2 minus 2. I get 0 over 0. Okay. Now the problem is that I can't factor these. On the top, I could factor out a 3, but still nothing will cancel top and bottom. So now you're going to try something called rationalizing. Rationalizing is a method that you're going to use every time you have a radical in the problem. Okay, if you see a radical, you know you're going to do rationalizing. If you forgot what rationalizing is multiplying by the conjugate of the part of the problem that has the square root. So in this problem, see how my square root's on the bottom? The conjugate of this denominator is 2 plus radical x. So in case you forgot what a conjugate is the exact same term, but the sign in the middle is flipped. So in this particular problem, you have 2 minus radical x. Its conjugate is 2 plus radical x. You don't have to write this down, but if it was 5 plus square root of 2, the conjugate of 5 plus square root of 2 is 5 minus square root of 2. So the conjugate, again, is review. It's very simple. Just change the sign in the middle. If I multiply by the bottom 2 plus radical x, I have to multiply the top 2 plus radical x. Okay. Now, this is why you multiply by the conjugate. If I FOIL the bottom, okay, if I FOIL the bottom, I get 2 times 2, which is 4, 2 times radical x, which is 2 radical x, negative radical x times 2, and negative radical x times radical x, which is minus x. In calculus, or what you saw that we just did, we multiplied, we FOILed. In this top part, I'm not going to FOIL because in calculus something may cancel. So unless they're conjugates, I'm not going to FOIL. So the top I'm going to leave by itself. Alright, now this is why you multiply by the conjugate. You'll notice that in the bottom, the middle terms, when I FOIL it, cancel each other out. So this whole thing can be simplified into 3x minus 12, 2 plus radical x, bottom is 4 minus x. Okay, still nothing cancels. But again, remember this first parentheses, as you notice, can be factored even more. I could factor out a 3, like so. Now, I'm in the same spot as the last problem. Do you see how this parentheses and the denominator look almost like they can cancel each other out? Yeah. So what I'm going to do, again, is I'm going to factor out a negative 1, and I'll factor it out from the numerator this time. So negative 3 minus x plus 4. So you notice that when I factor out a negative 1, it just changes the sign of the parentheses. 2 plus radical x all over 4 minus x. Now, top and bottom have a piece that they can cancel. And I'm left with negative 3 parentheses 2 plus radical x. It was a long process, but now that I canceled something, I can go back and plug in the number one more time. And this problem, my problem was 4, so I'm going to go back and try plugging in 4 again. If I plug in 4, I get negative 3. I get 2 plus 2 on the inside. Negative 3 times 4 is negative 12. Like so. The third and final piece is when you have fractions within a fraction. Okay, so let me show you what happens. I have x equals 0, or x goes to 0. I'll plug in 0 here, I'll plug in 0 here. I get 1/3 minus 1/3 over 0, which is 0 over 0. Okay, no good. I got to factor something. In this particular case, you'll notice that there's no square root, so I can't rationalize. You also notice that nothing factors, so I can't do that either. So this method is called simplifying. In simplifying, what I do is I'm going to make my numerator one fraction. Because right now, it's two fractions, this fraction and this fraction. Let's make it just one fraction. In case you forgot, remember fractions, I need to find a common denominator to combine a fraction. So the common denominator in this particular case is 3 plus x, which means on the left fraction, I need to multiply top and bottom by 3. The right fraction, I need to multiply top and bottom times 3 plus x. So this makes my new problem 3 over 3 plus x. So you notice, like in this problem, all I do is multiply 3 here and here. On the right, I'm going to multiply both by 3 plus x. So you notice now, in my numerator, I have a common denominator. When I have a common denominator, I can make these fractions, I can combine them into one. I have my common denominator, so I'm going to get 3 Now, be careful here. See, I have a 3 minus 3 plus x. Because this minus is here, this minus goes to both terms in the numerator. So 3 minus 3 minus x. On the bottom, I have my common denominator. Okay, so far? And that's all over that x that we had at the beginning. Now, the top can be simplified. I have a 3 minus 3. Those cancel out. It leaves me with a minus x. I still have my 3 plus x on the bottom. And then the gigantic bottom, I still have an x. So do you see in step 1 how I made my numerator, which was once 2 pieces or 2 terms, is now 1 term. Now we're going to simplify this fraction within the fraction by division. So remember this x here on the bottom? Remember, this is an x over an imaginary 1, right? That means the exact same thing. So to repeat, this is the original problem. This means the exact same thing as x over 1, right? Since I have a fraction, which is divided by another fraction, remember when you divide fractions, you flip and multiply. So this means the exact same thing as negative x over 3 plus x. So you see how this is just the first fraction right here? Multiplied by, remember you flip and multiply. Multiply by 1 over x. Okay, so that's that. You'll notice that on the top and bottom, I have an x that will cancel, top and bottom. Which means my final fraction looks like negative 1, because I'm multiplying across negative 1. And on the bottom, I just have this 3 plus x. So remember, in limits, once I'm done, all I do is go back to the original problem, which in this case it's 0, and plug it in like so. In this case, I get negative 1 over 3 times 3, which is 9. So I know it's confusing, but it's 4 steps that you can do for solving limits algebraically. You plug it in. If you get a 0 over 0, you're going to have to try either factoring, rationalizing, or in this case, simplifying a fraction in a fraction. There's 3 things that you need to know. Okay, the last piece for this video. I'm going to skip over the section C. So if you skip over in your notes till you get to the part where it says piecewise functions, it looks like this. When you do piecewise functions, it's exactly the same as we've been doing, like graphs. Exactly the same thing we've been doing as we're doing algebraically, but kind of combining the two. Okay? If you forgot what a piecewise function is, it is a function made up of 3 different functions. Okay? So do you see this is f of x, but it's made up of 3 functions. Function 1, function 2, and function 3. I'll even label it for you. Okay? How do you have a function made up of 3 functions? Well, function 1, when x is less than negative 3, I'm going to use this graph or this function. If the x is between negative 3 and 4, I'm going to use this function. And if x is greater than 4, I'm going to use this function instead. So it is a function made up of 3 different ones. And here are my intervals here on the right side. Okay. So really what I do is when I do limits, I find out which interval am I using it in. So this is the first example. It says as x goes to negative 5. So looking at 1, 2, or 3, do you see negative 5 has to fit into one of these? Negative 5 does not belong here, nor does negative 5 belong here. Negative 5 belongs here. Okay. If I have a possibility where negative 5 is just inside here, okay, if I get negative 5 and it's just inside here, all I have to do is plug it in. Okay. So I'm going to plug in negative 5. Like so. On the top, I get negative 10. And on the bottom, I get 0. Okay? And remember what I told you, if you get a number divided by 0, right now that is undefined. And I'll explain to you how to solve those later on. But for right now, if you get a number over 0, undefined. And that'll be the same for these ones, the next 2 also. So from the left is undefined, on the right is undefined. Now, next one is negative 3. Problem with negative 3 is, negative 3, you notice, I'm going to highlight with another color, negative 3 is here and it's here. It's in 2 different places. So what I'm going to do, if you have a piecewise function that I have to find the limit, I'm going to use it on both sides, both the left and the right. And if they match, that's the general limit. This one up here, let me highlight in a different color. this one up here means left of negative 3. This one down here means to the right of negative 3 or greater than negative 3. So that's why when I'm trying to solve for 3 minus, I'm going to use function number 1. And when I'm trying to find negative 3 plus, I'm going to use function number 2. So let's try it. Negative 3 minus, I will plug negative 3 into the first function. So that gives me 2 times negative 3. That gives me negative 3 plus 5 squared. That gives me negative 6 on the top. And on the bottom, that gives me 4, which gives me an answer of negative 3 over 2. Okay, so all I did was plug in negative 3 into function number 1. Now the second one, negative 3 plus. I will now plug it into function 2. I'm going to get negative 3 squared. I'm going to put minus a negative 3 over negative 3. When I solve this, I get 9 plus 3 over negative 3. I get 12 over negative 3, which is negative 4. Now, you see this particular one from the right does not match the one from the left, which means the general limit, again, does not exist. Let's look at 0 now. 0, you notice, only fits in function 2. 0 only goes in number 2. So I plug in 0. If I look at my function, I get 0 squared minus 0 over 0. You know you get 0 over 0. Not good. That means you got to do something else. Looking at this problem, we just went over the 3 things. I have to either rationalize, factor, or I have to simplify a fraction within a fraction. Of those 3 options, which one do you think applies to this function? This one is factoring. So, if I go back to my original problem, let me undo this. You know that the top has a common term of x, and the bottom is just x. And x in the top will cancel with the x on the bottom. So this whole problem is just equal to x minus 1. Now I plug in my 0. If I plug in 0, I get negative 1. So in this particular case, so in the last problem, when we did the negative 3, because it was in 2 different functions, because it was in function 1 and function 2, I had to do it here and figure out D and E. But for this problem and the first problem, because it was only in one function, okay, it applies for everything. Okay, so in this one, when I plug in 0, I get negative 1. Because it's only in function number 2, that means it's negative 1 for here and negative 1 for here. Okay. Two more. Number 4. You notice that 4 is in 2 functions this time. So again, I'm gonna have to plug in the left and the right. I'm gonna plug in 4 into function 2 first. 4 squared minus 4 over 4. This one I get 16 minus 4, which is 12 over 4, or I get 3. For the next one, 4 plus, I will plug in 4 into function number 3. This one I get radical. 2 times 4 is 8. 8 plus 1 is 9. I also get 3. In this case, limit on the left equal to the limit on the right, which means the answer is the same as that. And the last one for today, I have 13. You notice 13 only applies to this one, function number 3. 13 is greater than 4. So I'm going to plug it into this one and put it for the rest of the 3. If I put in 13, 13 times 2 is 26. 26 plus 1 is 27. This could be simplified to radical 9, radical 3, or 3 radical 3. And again, because it only applies to one function, it's the same for all of them. So that is standard 1. Can you solve for limits graphically, algebraically, and in piecewise functions? If you have any questions, again, you're going to put it at the end of this video lecture, and also you can ask me questions in class. If you have any questions that need individual attention, just raise your hand and I'll help you out that way as well. So thank you for watching and hope you have a great day.